Good morning, everyone. I am Nancy, and today I'll be presenting on the topic of exploring correlation, insights, and applications. Today, we will explore historical background, the different types of correlation, and the distinction between linear and non-linear correlations. We will also discuss common methods to find the correlation coefficient, look at the formula used to calculate it, and go over a real-world example to understand its application better. Additionally, we will touch on some advanced insights into correlation before wrapping up with a conclusion. Have you ever noticed how ice cream sales rise in the summer, just like the number of people visiting the beach? Or how practicing a skill more often helps you improve? These are examples of patterns that reflect a correlation fundamental concept in understanding relationships between variables. In simple terms, correlation measures the strength and direction of the relationship between two variables. It helps us understand how changes in one variable relate to change in another variable, whether they move together in a positive or negative direction. Let's dive deeper into how correlation works and its significance. Throughout the history, the concept of correlation has evolved significantly. In ancient times, civilizations like Babylonians and Greek observed relationships between celestial and earthly phenomena. Philosophers such as Aristotle explored causality and relationships, laying early foundations for understanding connections. In the 18th century, scholars began quantifying natural phenomena, which led to formal studies of correlation. By the 19th century, figures like Francis Galton and Carl Pearson advanced the field with groundbreaking work on human characteristics and statistical methods. Pearson developed the correlation coefficient, providing a standard measure for linear relationships. In the 20th century, the work of Charles Kurzman and Ronald Fisher further refined methods to measure correlations, even in non-linear data. Today, with the help of computers, we can analyze large data sets applying correlation across fields like finances, machine learning, psychology, and social sciences. Correlation comes in three main types. Positive correlation. This occurs when two variables move in the same direction. As one increases, the other also increases. A common example is the relationship between height and weight, where taller people tend to weigh more. Second is negative correlation. Here, variables move in opposite direction. As one variable increases, the other decreases. As an example, in the relationship between hours of study and the stress level, where more study time can lead to less stress. The third one is no correlation. In this case, there's no predictable linear relationship. Variables change independently of each other, such as the relationship between shoe size and the intelligence. There is no pattern to how these two variables relate. Now, let's briefly explore the two main types of correlation, linear and non-linear correlation. The linear correlation represents relationships where changes are proportional, forming a straight line in scatter plots. Common examples include weight versus height or stock prices versus market indices. It's measured by Pearson's correlation coefficient ranging from -1 to +1 and is widely used in the fields like economics and physical sciences. On the other hand, non-correlation involves relationships that are more complex, where changes are non-proportional. These are often visualized as curves or irregular patterns, like stress versus performance or enzyme activity versus temperature. Spearman rank is commonly used to measure this, and it's prevalent in biology, psychology, and complex system analysis. Correlation helps us understand how two variables are related. We can use Pearsman for linear relationships between continuous variables, as Pearsman rank correlation for non-linear relationships and ordinal data, and Kendall-Stau for ordinal data with small sample sizes or many ties. When choosing a method, consider data distribution, relationship type, outliers, sample size, and research context. Visualize data, check distribution, select the appropriate method, and interpret results cautiously. Now, correlation coefficients measures the strength and directions of relationship between two variables. They range from -1 to +1. The +1 means perfect positive correlation. The -1 means perfect negative correlation, and the 0 indicates no correlation. Here are three different formulas for correlation coefficients: one by Pearson correlation by Pearson, the second by Spearman rank, and the third by Kendall's. Now, let's have a look at the example problem. Imagine a nutritious curious about the connection between exercise and body weight. They gather data from 8 participants, noting their weekly exercise hour and body weight. Now, let's dive into the data. We have seen a range of exercise hours from 1 to 7 and a variety of body weights. By analyzing this data, we can uncover a possible relationship between these two variables. Let's walk through the process of calculating the correlation between exercise hours and body weight. First, we calculated the mean values for exercise hours, which is 3.75, and the body count, which is 71.375. Then we calculated the deviations from these means, followed by the product of deviations and the squared deviations for each variable. Using Carl Pearson correlation formula, we got the value of R as -0.987. This value indicates a very strong negative correlation. As exercise hours increases, body weight tends to decrease with a near perfect inverse relationship. So so it indicates that when the exercise R increases, the weight of the body decreases. In real world, correlation has its applications across various fields. For example, in economics, it predicts market trends and optimizes marketing strategies. In healthcare, it identifies risk factors like smoking and shows the benefits of vaccinations. In environmental sciences, it is used to study climate impacts and agriculture planning, while social sciences uncover links like parental education, boosting children's performance. The next application can be seen in psychology, where studies shows a negative correlation between stress level and sleep quality, highlighting the importance of managing stress for better sleep. And in technology, there's a positive correlation between website visit duration and conversion rates, suggesting long visits lead to more conversions. You can read other applications from this and the previous slides. Now, let's uncover some critical insights about correlation. First, the correlation doesn't imply causation. A related variable may not directly affect each other, as seen in the classical example of ice cream sales and drowning incidents. The second is be mindful of spurious correlations, where hidden factors like age influence variables like shoe size and reading abilities. Third is not all relationships are linear. Non-linear relationships capture complex patterns that linear correlation cannot. Other factors to watch out for include outliers, which can skew result. The multicollinearity, where high correlations among predictors cause redundancy, and the need of statistical significance, as small sample sizes might not yield reliable results. To enhance analysis, tools like correlation metrics help uncover relationships across multiple variables, while partial correlation isolates the effect of other factors. Lastly, time-lagged correlations and advanced visualizations provide deeper insights into trends and patterns. In short, understanding correlation is not just about numbers, it's about context, careful interpretation, and using the right tools. In conclusion, correlation analysis is a powerful tool that helps us understand the relationship between variables. It allows us to make predictions and inform decisions in various fields like business, healthcare, finance, and engineering. However, it's crucial to remember that correlation does not equal to causation. While correlation show connection, it doesn't prove cause and effects. It's important to be aware of limitations like outliers, multicollinearity, and spurious correlations, as can distort results. For complex data analysis, advanced methods like partial correlation and time-lagged correlation can provide deeper insights. And my final thought is correlation is a valuable tool, but its insight must be interpreted carefully within context. Thank you for your attention and time. I hope you find this presentation insightful and informative.